Hello, my name is Uwe Steinkrauss. I'm with a company called Unified Automation GmbH. It's located in Germany. We are doing toolkits and software development kits, so frameworks, libraries for integrating OPC UA into existing products. And we have those libraries in all different kind of languages, programming languages. And today I want to show you an introduction to the OPC Unified Architecture technology and give you some insights on the basic building blocks of OPC UA. And I want to start with a brief overview as an introduction, and then I come to some updates and some new enhancements that are already on the way in the OPC UA technology. So starting from the very first beginning, we have a technology that was called OPC, and today it's called OPC Classic because it's a legacy technology, and it is based on technology from Microsoft, which is called COM-DCOM, Distributed Object Model, and it was back 20 years the idea to connect process devices in the same way you connect printers today. So the idea was to have a driver that's installed on the Windows computer, and this driver is talking a proprietary protocol to the industrial device, but all applications running on the Windows box, they actually use the driver to communicate to this particular device. Same concept than you have with a printer and printer driver. And there were functionality to access data, to access historical data, and to get notifications for alarms and events. And based on this technology, there were new requirements coming up, and that was the reason why OPC UA, the new generation OPC technology, was developed. And on the one side, we have the wide adoption of OPC Classic, but we want to use OPC as a common system interface. And to do that, we need something, we call it scalability. It means that you can use the technology on very small embedded devices, but use the same technology as well on larger systems like MES ERP systems or the classic SCADA systems. In addition to that scalability, for the communication between distributed systems, we also need platform independent. We need a technology that can be implemented on any kind of operating system, not only on Microsoft. And the reason because of that, we don't bind it anymore to COM-DCOM. We have a complete new platform independent application, and we can implement it on all kind of operating systems. In industry, we also need redundancy. We also need very fault-tolerant system, very robust systems. They need to run 24/7. And of course, performance is not an option. We need very, very high performance to transfer all the data coming from the process devices. And as you all know, security becomes more and more important. So we need to secure the data, we need to encrypt, we need to sign the data, we need to authenticate data to ensure that only authorized persons can actually see the data and work with the data. And we need to cross firewall boundaries because we want to interconnect devices in large networks and even over the internet. In addition to those more protocol-specific details, we also need data modeling capabilities. This is one of the basic key features of OPC Unified Architecture. And we need that to describe the data that is inside the machinery. So we need a type system to describe types, and we need to describe instances. I will come to that on later slides. We have complex data structures that we need to transfer, and to describe all the information, we need a metadata model, and this metadata model is used to describe the semantics and all the relationship between the data inside this particular device. And with that concept, we describe all kinds of data. One of the pictures you will see on Wikipedia and everywhere is the picture here with the basic building blocks. And I want to step through all of those to give you an overview what they mean and where the technology comes from. We started in 2003, and until 2006 was a definition phase, so writing the specification. And then there was a verification phase where we tried to implement what was specified to see if it's actually doable in writing the technology in code. And the final release of the specification was then in 2009, and that was the time the first products showed up on the market. And now the OPC Unified Architecture is also an IEC standard, so it's an international standard, and that was released in 2010. So as a basic overview, OPC UA is the established classic OPC standards and features, data access, historical access, alarms, plus platform independence, plus it's using now IP-based standard protocols, and it has inbuilt security features. And we have a generic object model which we can use to describe any kind of data. And we have an extendable type system, so we can, over time, extend the description of the information. And the whole technology is scalable, and that is done through profiles. I will come to that a little bit later. And of course, we will not cut off the old OPC implementations. So there's a migration path from the classic OPC to the new unified architecture. As I mentioned, the object model and the type system, that is one of the basic building blocks. And that's a little blue one here on the side. Modeling data and the capabilities is best described, it's same like an object-oriented programming language. So there's an OPC UA object, which is a representation of a data point or some processed value, and it has a variable, and it can have methods, and it can have events and fire events, and this is a complex object. And as you can see in the variables, that is the functionality we had before with OPC data access and historical data access. And the events, that's what we had and called OPC alarm and events. And the commands that are method invocation of those kind of objects. Everything in OPC UA is a node. So the address space of an OPC server gives you the full description of the information that is inside this device. And all this is described with nodes, and there are 8 node classes defined by the OPC foundations. That is the base node classes, and from this, everything else is derived. And in addition to the nodes and the base nodes and all the attributes, you can extend this system over time. And if you have special requirements, you can add that by deriving from the base node. And there's a description language, a graphical description that was defined to describe those things graphically. This is more or less same like you maybe know from the UML description of object-oriented models. And we have instances of objects, variables, methods, and we have object types. The types are the ones with a shadow underneath to see the difference between a type and an instance. All the objects and all the nodes inside the address space of an OPC server are then interconnected with references. So references are like pointers pointing to another node. And with those references, we can now model all the relationship between the different nodes inside the address space. I will give you here a very short example just for overview. So imagine we have this object type, which is more or less like a class for the programmers. Inside the object type system, we have the base object type, and from that we now have a look at the analog measurement type. The analog measurement type is defined by the OPC Foundation, and it describes any kind of analog measurement. So this type is already inside the data access information model. And it consists of a system alarm, of a level alarm. It has, of course, the measurement itself, where we can find the value, the measurement value. And the value has then properties like instrument range, EU range, and the engineering unit. So if the measurement is a temperature, then the variable will be 25, and the engineering unit will be degrees Celsius. So with that, we can describe the whole analog measurement. Now, having this analog measurement type in the server describing how the type looks like, we now have, of course, more measurements inside our device. And as you can see here, there's one object instance. In the end, there are already three. So it's temperature 1, temperature 2, and pressure. And to show you how the pressure measurement looks like, it looks exactly the same than the type. And it has a reference in the type system to demonstrate that it belongs to that type. And of course, now the pressure measurement has a value and has an engineering unit and has an alarm, so it can fire a level alarm if the pressure is too high or too low. And by this, the information gets fully described in an OPC UA way. So the big question is, why are we doing all this? So now imagine you have a SCADA system that needs to display measurement. You can have a faceplate, a graphical representation that can display analog measurements. And you only need to design that once, because if it knows how the type looks like, it can adapt to that type, and it now can show all different instances of measurements, no matter if it's a temperature or pressure or whatever. So we have faceplate, graphical display that belong to types, and by this, the engineering can be reduced immensely, because we just need to connect the type once, and then everything else gets connected automatically. So the engineering is much, much faster. The next basic building block is the transport. That's a little red one on the side. There are different transport bindings. So OPC UA can be transported over different, maybe protocols. We say transports. And one of the transport is mandatory. That's one every OPC UA server must implement. That's the one with the green arrow here. It's the optimized OPC UA binary. And this is using TCP/IP as a base, so it's sitting on top of TCP/IP. And then it defines a UA TCP protocol. On top of that, we have a security layer, which we call UA Secure Conversation Layer. That's the layer that encrypts the message. And on top of that is the encoding, which is a UA binary encoding, is a special encoding, which is very optimized for the use of OPC. On the side, you can see a second binding, which is an optional binding. We call it XML Web Service binding. It uses XML encoding. And for the security layer, it uses the WS Secure Conversation. And then it's a SOAP envelope around it. And then it's sent over HTTP. Those two we call the message security, because the message content is secured. You can now transport the secured message over an insecure transport channel. So you can transport over HTTP or TCP because the message itself is already secured. In contrast to that, we have, since version 1.02, 2 more bindings and 2 more transport bindings. And as you can see here, they are optional. And those transports use the transport security. So we use an HTTPS, TLS encrypted HTTP. So we have an already secured transport. And over that, we can now just transfer the UA binary raw data directly, because the transport channel is already secured. It's a transport security. And then you can transfer this over port 443, like all the other HTTPS traffic as well. And then there's another one with SOAP and XML encoding. But those are optional. The mandatory one is the green one. That is in every OPC UA component, must be implemented, the binary, optimized binary protocol. And as you can see, because of this layered architecture separating the transport from the secure and from the encoding, all these different layers can be exchanged and enhanced over time. So we can add more protocol bindings over time, and we do actually, I will show you later. And this is not changing anything in the rest of OPC. It's just the way how to transport the data. And this also gives you very much flexibility in this technology. Now I want to take a very close look into a protocol stack. So on the left side, I have a client application, and that client application calls an API on the stack. It's an API call, and we have this stack in different programming languages. It's available in NCC, it's available in .NET, C#, and it's available in Java. And there's an API call, and the client application calls into the stack. And then the message structure gets encoded, and the encoded message then gets secured. And the secured message gets transported over the wire. And on the other side, the message goes up the stack through the different layers. So the transport header is removed, then the message is decrypted, and then the raw message structure pops out on the server API. And if the server answers, it goes the same way back and gets transported over the wire again. And this is the concept of transferring data from a client to a server and back. And here you can see the different layers, message encoding, security, and transport, which is all implemented in the stack. And the good thing to know it, you don't need to implement those stacks, because those stacks are already available from the OPC Foundation in 3 programming languages, and you just pick the one that you need to integrate in your application. On top of these 2 basic building blocks, we have the UA-based services. The services are, actually there are more services, 36 services, and we group them into service sets. And these service sets gives you access to the data. And these services, they are grouped like for discovery features, so finding out who's on the network, how to connect to the OPC server. Then there is services to browse through the address space so that you can have a look at all the nodes and figure out how they all belong together. So you can browse into the instance system, but also into the type system. And so if a client connects to a server, it can discover this server and can investigate everything that this server knows by just connecting to it and browsing through the address space. Then, of course, most important, we have read and write services to access information, to access the process value, to access the attribute, the value attribute of a node. And so we can read the temperature and write data to the server. In addition, there are history functions. So we also can read history of certain data points, which gives you a time frame of data that was recorded for this particular node. And we have history for events as well. In addition, there are method calls. So if a server provides a method, then the client can invoke that method, and then the server is doing something, and then gives you a callback if it's done. And of course, we have the data change mechanism. Most people know from the classic OPC. This is now called subscription, and the subscription has monitored data, and this data is transferred when the data is changed. So we only transfer the data when the data has changed. We don't need to cyclically transfer the same data all the time, because we already know it. And because of that, we only transfer when the data is changing. And the same mechanism we, of course, use for events. So the notification is only transported over the wire when it actually occurs. And in addition, then there are services for creating and deleting nodes. So this is something to configure a server. Those generic services are fixed and are defined by the OPC Foundation. They are just this set of 36 services. With that, we can do everything. And the reason why they are fixed is because only then it works plug and play out of the box. Every client and every server, they just use these services. The flexibility in OPC comes from the information model. So by describing data, by creating an information model, that's where the flexibility of OPC comes from. But the access is defined and always the same. And those are the base services. And for the information models, we have already built-in information models that are defined by the OPC Foundation. And we have an information model for data access. And it's for representing processed data in an industrial device. And one of the types that is already defined there is the analog item type, which I showed few slides before. In addition, there's an alarm and condition information model already defined by the OPC Foundation. It's for representing conditional alarms, process alarms. We have state machines for alarms, how an alarm becomes active and gets acknowledged and becomes inactive. All these state machines are already defined by the OPC Foundation. You can just use them. And of course, there are methods for giving feedback to, for example, acknowledge alarms. Then we have historical access. So we have information models for describing historical data, history of data, and also history of events. And the programs is for method invocation and state machines that are started by a client. So you can invoke a method inside a server, and then the server is doing something. So these are already there, information models already defined by the OPC Foundation. On top of that, we have companion models. Other standardization organizations use OPC technology, and they just describe their data in a companion specification. They describe it in an OPC UA way of describing data. And you can do that on top of the standard models that are already defined by the OPC Foundation, but you can also do it directly. And there are some very successful companion specifications that were already released. One of the early ones was a PLC Open. So the PLC Open group, the standardization group, sit down and defined how PLC data is exposed in OPC UA objects. But there are also other groups, like from building automation, a BugNet group has defined a companion mapping specification. We also have auto identification, RFID readers that have an information model specified on top of OPC. And there are others ongoing and already finished. Automation ML is one of those. The oil and gas industry for subsea has defined a certain set of data and information as a companion specification. On top of those companion specifications, you can also define your own information model, which we then call the vendor-specific information model. So if there's still stuff you need, but it's not already in a standardized model, then you can create your own. So you can create your own vendor-specific models on top. And that is the whole building blocks OPC UA is made of. The OPC specification has currently 14 parts. The ones in blue here, that are the base core specifications. It's a lot of paper, so if you want to read it, it's public available also as an IEC standard. The most important parts to read is part 4. It describes the services, how they look like, and part 6, the mapping on the protocol. And then there's a profile specification. I come to that in a minute. There's a new specification going on. It's part 14. It's a pub sub specification. It's in the utility type specification. And so this is enhanced over time, but the core specifications are already there. So talking about scalability, how to create now a server with a certain functionality. The OPC Foundation has defined conformance units and profiles. Conformance units are the smallest parts of functionality you can imagine and you can test. So it's a unique functionality. And now we group conformance unit and we form a profile. A profile is something you need for a certain feature. So with this concept, we can, on the one hand, test the functionality and certify the functionality, but also we can describe the functionality of a server in terms of profiles. To give you an example, here I have the standard UA server profile. And as you can see, it consists of an address space. So every standard UA server must have an address space. It must support data access functionality, so read and write of attributes. It must support security, encryption of data. And it must support the binary protocol. So with that, we have described the functionality of a standard UA server. On top of this full-featured profile, you now can have different facets describing more functionality. For example, the event subscription facet and the message server facet. So now this server can fire events, and it has methods to acknowledge those events. And that, of course, gives you alarms on condition functionality. And in addition to that, you can have other profiles and facets building on top of a standard profile, which is historical access, complex data, redundancy, or even your companion specification models that can add features and facets here. So with this concept of profiles and conformance units, we can describe the functionality of a server. If you start development of a standard server, then the server must support connect, of course. It must support browse to look into the address space. It must support read and write, and it must support the subscription. And here we have the server with those base services, and it has a variable inside. And if you now want to extend this standard OPC UA server with a pure data access functionality to make it an historical data access server, you only need to add one additional service, which is the history read service. And then in your information model, you change the attribute. As you can see here, it has access level history read, and the historizing attribute is true, indicating that for this particular variable, there is history available. And now a client that reads and browses and looks into this server figures out, okay, there's a variable, I'm interested in that. By reading out the attribute, you can find out, oh, for this variable we have historical data, and then you know, okay, now I can call the history read function and to get the historical data that was recorded for this variable. So this is the basic concept. To get a description on all the different profiles and all the different facets and conformance unit, there's a website. It's opcfoundation.org profile reporting, where you can see all the different profiles and a description, what it means and what functionality is included in that profile. And as you can imagine, profiles are building up on top of each other to create more and more and more functionality. There are very small profiles as well. There's an embedded and a nano server profile, micro server profile, describing a very, very small set of functionality. And that OPC server then is very small and can run in a very small, limited, embedded device, like, for example, a very small sensor. In addition, we have something like file transfer for OPC, or in an OPC way of thinking, it's just an extension to the information model. So as you know, a file API from every programming language, open, close, read, and write to a file. The same concept is here in an OPC UA representation. We also have folders and files, and there are methods to read and write. And you can, by this, have no limitation in file size, and you can transfer data files from a client to a server. And you can read and write, and by this you transfer the file. So you can have an OPC server that is representing a hard drive of your computer. More functionality, and we call it a LDS. It's a local discovery service. It's an OPC server, a UA server, that is just there to represent and to show what other OPC servers are installed on this machine. So the LDS is something similar to the classic OPC enum. So it shows locally if there are more OPC server, more than one installed on one box, then the LDS will give the client the information which OPC servers are there and how to connect to them. So the client always is doing the same. It always connects, finds the servers, and then gets the endpoint description to connect to it. And the OPC servers, if there are more than one on one box, they register at the LDS to give the information how to connect to them. And the LDS and the standard port that is always used is 4840. It's also registered at the INA, and so it's a standard port for OPC UA. So every client knows that and can connect and find out. There's an extension to that. It's an extended LDS, which also has the functionality for name resolution in a network. So you could even use that in a network where you have no regular domain name server. Then this LDS will also do the name resolution for you. This only works in local subnet if you have no central infrastructure. In even larger systems, there's another concept that is called the global directory server. It's more like a domain controller. So in one network, you have one global directory server, and there all the OPC servers and all the clients can register. And so they announce themselves to that GDS. And so if you connect as a client to the GDS, you will get the full picture of every OPC component in that network. In addition, the GDS has another functionality. It also handles certificates and distributes and rolls out the trust list for all the components. So it's also a central management point for all the trust relationship and the security information for the different OPC components in that network. This GDS can act as a certificate authority, and it can push and pull certificates into the other servers in the network, keep them up to date, and configure the security. There's already a product available on the market, and we expect more to come. Some new enhancement to OPC, and that is what I want to talk about now for the future enhancements and what is coming up next. We have the classic client-server model with the services and the protocols. And on the other side, we have a pub-sub model, which is a different communication mechanism based on broadcasting messages. And I will explain how this works and what we're doing there. So the service-oriented request-response approach through OPC and through TCP is using a peer-to-peer connection where the client and the server know each other, and then they build up a session, and then they communicate in the context of that session. And this is very good and scales very good, and you can use it, and it's already there, and it works fine. You have a data change mechanism because in the context of the session, both components know each other. They can monitor the lifetime on the other side. They figure out if there's a failure, if the other component is dying or not available, and then they can react on that. And this concept works very good inside machinery, on the plant floor, but it scales only very good if you have only one-to-one connections, or if you have like 1 to 20, 100, maybe 200 connections running, then this works very good. But if you go in a different scenario where you have one server, but you have thousands or more than 1,000 clients that are all interested in data, then having a single connection to every communication partner is very resource consuming for the server. And for that, it's better to use a broadcast approach. So sending out the information once, and everybody who's interested can just listen to it. That is the pub-sub mechanism. For both, we have use cases today. And so what I want to show you here is an OPC UA server application that has implemented both communication mechanisms. On the left side, you can see the client-server request response. We have the client A, and that has created a session inside the server, and has created a subscription there, and it has registered monitored items which coming from the address space that are the nodes of interests that are monitored. And now if the data changes, then the server will publish the information to this client. Now you can imagine if you have on the left side even more, not only one client, more clients, then each client will create a session and will create his own subscription. And so you need more and more memory resources inside the server to handle all this communication. On the right side, you can see the other concept where the data frame is already set. It's a data set that's already configured. It consists of different nodes from the address space. And this information is then broadcasted out to the network. And now we can have many subscribers who are interested in this information. They can just listen to it and pick the information they want from this message stream coming out of the server. But for the server, it's much simpler because the server is just pushing out the same data all the time and only once, independent on the number of subscribers that are interested in this information. So this gives you an overview on the two different ways of communicating with OPC UA. On the one hand, we have the request response based on a session, and on the other side, we have published subscribed based on broadcast of information. The big question is, why are we doing this? So there are use cases why we need this extension to the communication. And the one use case is driven by machine-to-machine communication. In the case where we need very fast communication of maybe only few data, but very fast communication, and where we have the situation where one entity needs to communicate to many others, then this pops up, makes sense, so the server can send out the data once and many can listen. And if we do that very, very fast, and if we then do it cyclically, and if we then do it always in the same cycle, deterministic, then we can even have real-time communication with this approach. So this is the use case for machine-to-machine communication in real time, where we can use the cyclic broadcasting in a time-sliced way. And for that, at the moment, we are looking at TSN, time-sensitive network, which is giving you a time-sliced Ethernet, and then you can transport the information over this time-sliced Ethernet and get real-time, deterministic real-time. Then there's a second use case, which is also very useful. It's driven by the Internet of Things. So the IoT use case, where you have many, many publishers of information, and you have one consumer of the information, which is obviously the cloud. So you have a many-to-one communication. In that case, also it's very good to have this pops up, because here you can see I have many OPC UA publishers. They're all publishing the information to one relay, and this relay broker then creates the message, for example, in AMQP or MQTT or whatever cloud-based protocol, and then sends the information to the cloud. And the cloud then is a subscriber receiving this information. And this can then be used in a global network, which typically you have if you are in a cloud infrastructure. So these are the two use cases for PubSub. As a summary, and what you need to remember for the technical introduction, is OPC UA stands for Data Modeling Capabilities, which is like an object-oriented programming language, so you can describe any kind of information with a generic object model. Then there's the communication part, where we have integrated security, where we have different protocols, different protocol bindings, and we use standard internet-based protocols. We use TCP, basically. And we have a fault-tolerant communication, very robust, and we have redundancy concepts in that as well. And then the fourth basic block is a collaboration. So other standardization organizations and other standard bodies defining their own information models, sitting on top of OPC UA and using OPC UA as a transport mechanism and as a description mechanism for their data. And of course, there are new applications and use cases coming up, and those are addressed with the PubSub. So the one-to-many and many-to-one communication using broadcasting and time slicing in Ethernet, so TSN, for deterministic real-time. So with that, I'm done with my presentation on the technical introduction. If you have any more questions, here's my contact data. You can write me an email or call me, and then I'm happy to talk about more details on the technology with you directly. Thank you very much.